Welcome to this lecture series in group theory. We are starting a new module, and this module will be about permutation groups. Previously, we had a module about cyclic groups, which are an example of a simplest family of groups. On the other hand, permutation groups are an example of a most complicated family of groups. So let's recall a few definitions. Suppose X is a set, then this we defined as the set of all bijections from X to X, equipped with the binary operation of composition. And we saw that this is a group, and it was one of the first example of groups. This is called the symmetric group of X or the permutation group of X. I don't think I used this phraseology earlier, but I think this is a better phraseology, and I would like to stick to this one from now on. The elements of this guy are called permutations of X, so another terminology. And as a piece of notation, instead of writing this hefty thing, we just write that. Okay, so let us introduce a notation to what do I say? To denote permutations. So suppose sigma is an element of S4 given by that. So we can alternatively denote sigma as this 2 cross 4 matrix. And this matrix has nothing to do with linear algebra. It just happens to be a matrix. So, okay, let me write this down in real time. Sigma 1 is 2. So we just write a 2 below 1. Sigma 2 is 3. So we write a 3 below 2. Sigma 3 is 4. And sigma 4 is 1. So it's more or less a decoratively new way to write sigma. It's just more convenient. Okay. In general, if we have sigma in Sn, then this is the notation for sigma. So let's take an example and compute something. Suppose sigma and gamma were in S5 given by these. Then let us compute that. And again, let me do it in real time. So gamma sigma is what we want to compute. So if I feed 1 to gamma sigma, I get gamma of sigma of 1. So we just need to find sigma 1 and then feed that to gamma. Sigma 1 is 2. We feed 2 to gamma, we get 4. So this is a 4. Sigma 2 is 4 and gamma 4 is 2. So this is a 2. Sigma 3 is 3 and gamma 3 is 1. So this is a 1 and 4 goes to 5 goes to 3 and this is a 5. So it helps do things quickly. Anyway, so now for another way to denote permutations, and this is the main topic of this lecture, the cycle representation or the cycle decomposition of a permutation. So let's introduce that by way of an example. Suppose sigma is an element of S8 given by that. Then first let us have a graphical representation of sigma. So 1 maps to 3. We will draw an arrow from 1 to 3. Okay. Now we go to 3 and 3 maps to 7. So we draw an arrow from 3 to 7. 7 maps to 4. And 4 maps back to 1. So we get this cycle. Okay. Now 2 we need to consider. So 2 goes to 5. 2 goes to 5. And 5 goes back to 2. Therefore, we need to make another arrow. So we have captured that. And 6 is left fixed and 8 is left fixed. So for that, we have two different colors again. Right, so this whole graph captures completely what sigma is. You can recover sigma using this graph. But drawing this graph every time, it would be very expensive. So we can denote what happened in this graph in a different way, in a lexical way. So all we do is we just record these cycles. So 1 goes to 3, 3 goes to 7, 7 goes to 4. So this is the white cycle. The yellow cycle is 2 goes to 5 and 5 goes back to 2. So basically we are writing things in a cyclical way. 1 goes to 3, 3 goes to 7, 7 goes to 4 and 4 goes back to 1. 2 goes to 5, 5 goes to 2. And then there are these 1 cycles. Maybe I should put a comma here. So let me put a comma here. And then there are these single cycles. So this is what sigma is really. This completely captures what sigma is. And of course, this is more compact than that, but we will further compactify it. So first of all, what we will do is we will not write these trivial cycles. If we remember that sigma is an element of S8, writing these trivial cycles is unnecessary. So we can just write 1, 3, 7, 4 and 2, 5. So the above thing, this thing captures everything that sigma is trying to tell us, provided we remember that sigma is an element of S8, with the convention that the numbers that do not appear here lie in single cycles, meaning they are left fixed by sigma. So this is further compactification of this notation. But we will even further compactify it. But to get there, first let us make a computation. So suppose we have sigma and tau elements of S9, right? They are elements of S9. So first let us write them in this cycle notation, or the preliminary cycle notation. So we start with 1. 1 maps to 2 under sigma. 1 maps to 2, 2 maps to 3, 3 maps to 1. So this is one of the cycles that sigma is holding. Then we have 4 maps to 5 and 5 maps to 4. So 4 comma 5. We don't really write commas here, although we could, but the spacing is enough to delineate what is what. Okay, and all of these things are left fixed by sigma, so we don't even write them. So this is sigma, provided we remember sigma is an element of S9. Tau is what tau is. All of these are fixed. 1, 2, 3, 4, 5, they are fixed. 6 maps to 9, then 8, then 7, and then 6. So there's a 4 cycle here. 6, 9, 8, 7, and then 7 maps back to 6. So that's what tau is. And now let us compute what is sigma tau. Sigma tau is the product that product. So we need to find out what is the image of 1, what is the image of 2, and so on. Now, note that whatever sigma is disturbing, meaning whatever sigma is not fixing, is fixed by tau, right? No numbers that are present in this non-trivial cycles are present in non-trivial cycles of tau. And conversely, if there is something in the non-trivial cycle of tau, it's not present in non-trivial cycles of sigma. So if you just think about it, what you will get is this product is very simple to compute. Just push it inside the bracket, that thing, right? So this is a very simple check. And this suggests that we can further compactify our notation, because what is this guy? This guy is really, as we just saw, is the product of these two things. It is really the product of these two cycles, or rather these two permutations. This is a permutation, that is a permutation, and this guy is the product of those things. So therefore, we can just get rid of these brackets and finally converge upon this notation, that instead of writing all those extra brackets, we just denote sigma in this way. So to wrap it up, you have some permutation sigma. You find out all the non-trivial cycles in sigma. They will be disjoint necessarily, and just write those cycles in this fashion side by side. There could be many. In this example, there are only 2 non-trivial cycles. There could be many. We have the convention that we do not write anything that's there in one cycle, although you could if you really wanted. There is nothing wrong with writing them, but you can drop them, provided we remember what is the alphabet on which sigma is operating. Okay, so this is the cycle representation of sigma, and it's very, very convenient. And we should recognize that this can also be thought of as a product of this permutation with that permutation. Okay. So now let us make a few notes. So this is what we saw. Every permutation can be written as the product of disjoint cycles, whereby a cycle we mean a permutation of this sort whose cycle representation features only one non-trivial cycle. So that's what a cycle is. When we say a permutation is a cycle, we just mean it is a permutation whose cycle representation has exactly one non-trivial cycle. It could be trivial cycles because it could be fixing a lot of things, but there is only one non-trivial cycle and it looks like that. for some k greater than equal to 2. Two disjoint cycles commute. So if I have a cycle a1 up to ak and another cycle b1 up to bl, and they are disjoint in the sense that none of the ai's is equal to any of the bj's, then you product them in this way or you product them in the other way. If you first do the b's and then the a's, it's the same thing. And that's a trivial comment because whatever this guy is disturbing, this guy has nothing to do with, and conversely. So you see that they will agree on every letter of the alphabet. This is a simple remark. The order of a k cycle is k. And this is very simple because you have, for instance, this 4 cycle. Suppose this was my permutation, just this 4 cycle, everything was being fixed. Then taking this to the power 4 means you start with 1 and move it 4 times. You get back to 1. You start with 3, you move it 4 times, you get back to 3, and so on. So that's what this is saying. The order of a k cycle is k. As an example, I highly recommend you compute. Suppose sigma is 1, 2, 3. Suppose sigma is this cycle lying in some Sn, doesn't matter, n greater than equal to 3. Compute sigma cube explicitly. We know it is going to be the identity permutation, but compute this. Okay. Let me compute sigma square. Sigma square is 1, 2, 3 times 1, 2, 3. So 1 maps to 2 and 2 maps to 3. So here we will get 1 maps to 3. 3 goes to 1, and then 1 when fed here goes to 2. So this is 2. And 2 maps to 3, 3 maps to 1. So it closes back because 2 maps to therefore 1, and this is your sigma square. So cycle representation also facilitates computation. Anyway, also note that this cycle is same as that cycle. So in particular, what I'm trying to say is 1, 3, 5, let's say whatever, 7, this cycle is same as 3, 5, 7, 1 because it is carrying exactly the same information. This is saying that 1 maps to 3, 3 maps to 5, 5 maps to 7, 7 maps to 1. This is saying 3 maps to 5, 5 maps to 7, 7 maps to 1, and 1 maps to 3, which is exactly the same thing as the previous one. So you can kind of cyclically permute, no pun intended, and rearrange things in this fashion. Okay. So here is a very nice thing that you can compute the order of a permutation just by looking at the cycle representation. So this claims that the order of a permutation sigma is the LCM of the lengths of all the cycles in the cycle decomposition or the cycle representation of sigma. Okay. So instead, or rather, in fact, we can just write all the non-trivial cycles. It's the same thing because the trivial cycles have length 1, and to the LCM they don't really matter. So either you say all the cycles or all the non-trivial cycles. It's the same statement. Okay, so let me illustrate this not in full generality, but suppose we have, say, how shall I start? So let say sigma is a1 up to ak and b1 up to bl. Let's say there are only 2 non-trivial cycles in sigma. I will do the proof in this case, and the more general case where you could have even more cycles, it's very, very similar. So I won't do that. Before I go ahead, note that if sigma had only one cycle, then it is saying that the order of sigma is just the length of that one cycle, which is already this statement. That is the statement. So if there were only one cycle, we have already seen that this statement is true. Okay, so here we want to show that the order of sigma is the LCM of k and L. Okay, so first note that. Let us call this gamma, and let us call this theta. So order of gamma is k, because gamma is a k cycle, and order of theta is L. Okay. Gamma and theta commute because they are disjoint cycles. Why are they disjoint? Because this is the cycle representation of sigma, and 2 non-trivial cycles or any 2 cycles in a cycle representation are disjoint. So none of the AIs is any of the BJs. So gamma theta is theta gamma, and therefore, thus, gamma theta to the power any integer, let's say m, is gamma to the m theta to the m. And from here it is immediate that gamma theta to the power LCM k comma L is equal to identity, because if you feed the LCM in place of m, this becomes identity because of course k divides this guy, k being order of gamma, and similarly this also becomes identity. So therefore this part is clear. So what we conclude from this is that order of sigma, which is same as gamma theta, is at most the LCM. Okay, now suppose gamma theta to the power d, or let me continue to use m, suppose this is identity, then gamma to the m and theta to the m is also identity. And the interesting maneuver is that this implies gamma to the m is identity and theta to the m is identity. So why is that? Well, the things that gamma to the m disturbs are the AIs. It fixes everything else. And the things that theta to the m disturbs are the BJs. It fixes everything else. So if this were not identity, then there is some AI which it is moving to, let's say, AI prime. And the same AI will also be moved by this guy, because this guy fixes AI, and the resulting thing when fed here, which is AI, becomes AI prime. So if this were not identity, then this product couldn't have been identity. And if this were not identity, then this product couldn't have been identity. So make sure you follow that point. And this implies k divides m and L divides m, which implies m is at least the LCM of k and L. And putting these two things together, we get that the order of sigma is LCM of k and L. And you can generalize for arbitrary product of cycles. Okay, so that's very nice. And let us make an example computation, which I won't do in full, but here is the thing. We compute the number of elements of order 3 in in S7. So by the previous proposition, any element of order 3 in S7 will either look like this, meaning in the cycle representation, it will either look like this, or it will look like that. How many things of this sort are there? There are 7 options for this, then 6 for this, and 5 for them. So it's 7 times 6 times 5. But recall that you can cyclically permute them and it's the same thing, meaning this is same as A2, A1, A2, A3, A1, and so on. So we have overcounted 3 times, and hence we need to divide by 3. So many are such elements in S7. How about that? We have 7 options for this one, 6 for the next, 5 for the next, 4 and then 3 and then 2. But again, here we have an overcounting of 3 times, so we divide by 3. Here we have an overcounting of 3 times, so we divide by 3. But overall, there is another overcounting of 2 times because these two things can be switched. So there has to be an extra factor of half. So the first one is 70 and the second one is 70 into 4. So that is 350. Right, so I did not do full explanation of why divide by 3 and why divide by half and so on, but I gave a general hint as to what is going on. And the point I want to convey is that the cycle representation facilitates such computation. The number of elements of order 3 in S7, it's not so simple if you think about it. But we can compute it in no time. Okay, so this is the end of this lecture. As usual, like, comment, share, subscribe. I also have Patreon. The link is in the description below. Thank you for listening, and I'll see you next time.